Hi, so finally we can put together a lot of things we have so far and state the continuity lemma, which will connect the convergence of the characteristic functions to weak convergence. Continuity lemma, nevertheless I'm going to call this a theorem, it's pretty important. Continuity lemma. So let mu n be a sequence of distributions on R, and the associated characteristic functions are phi. Alright, and it has two parts. Part 1, if the mu n's converge weakly to some measure mu, then there is pointwise convergence of the characteristic function. So phi n will converge to phi at every t as n goes to infinity, where phi is the characteristic function associated to mu. So integral of e to the itx d mu x, the characteristic function of mu. Okay, so that's part 1. That's not the important part. The important part is part 2, which is the following. If for every t in R we have that there is a limit of the characteristic function phi n's as n goes to infinity, which I'm going to call phi t, so that's the definition of my phi t. If this thing exists for every t, and the limit is continuous at 0, this limit function phi is continuous at t equals 0, then we have weak convergence. So then, in fact, then phi is a characteristic function of a distribution which I'm going to call mu, and the sequence mu n converges to this mu weakly. And that's the important bit. So convergence of the characteristic functions will imply convergence, weak convergence of the distributions. Let's prove this theorem. We now have everything we need for that. One is trivial. One of the, again, we've seen this before. One of the definitions of weak convergence is that bounded continuous functions like e to the itx converge under the integral according to that measure. So that's trivial. The important bit is 2. So the first thing I'm going to show you is that mu is tight. And again, the assumption is only that we have limit of the characteristic functions and it's continuous at t equals to 0. So mu is tight. Why is that true? Now, if I take mu n of the real line minus 1 over a and 1 over a, I'm going to work with the open interval, but of course you can always close it by adding a little bit extra. So it doesn't really matter that this is not compact because of openness. The main point is that it's finite. Okay, so what is this? This is the integral of the measure mu n on exactly this set, which means that x is larger than or equal to 1 over a. What I want to show for tightness is that this is bounded uniformly in n, okay? And that's where lemma 3 comes handy, because lemma 3 exactly told us that there is a k that works for every a and every distribution, so that we have this bound here. So there is a k by lemma 3 that works for every mu n at the same time. This is smaller than or equal to k over a, integrate from 0 to a, 1 minus real part phi n with respect to t. That was lemma 3. Okay, Now these guys again in mod are smaller than or equal to 2. If I integrate 2 from 0 to a, that's finite, so I can use dominated convergence, and as n goes to infinity I have convergence of the phi ends to phi by assumption, and dominated convergence can bring this limit out of the integral, and therefore I have a convergence here to the same integral using the limiting phi, 1 minus real value of phi dt. And now what I want to take, of course, is a limit in a. So I want to show that this is bounded uniformly in n and going to 0 as a goes to infinity. Uniformity I already have because the supremum of it is bounded, because there is no n on the right hand side, so I found the bound uniform in n so far. But I also want to show that this bound is small. If you look at phi at 0, phi at 0 is 1, so real part of phi at 0 is also 1, 1 minus that is 0, so this integrand is 0 as a is getting very small. Okay, now the integral from 0 to a divided by a is the average value of the function. The average value for a continuous function converges to the function value itself as I take the interval shorter and shorter. So as a goes to 0, if I take a to 0 here, because of the continuity of phi, and therefore continuity of 1 minus real value phi, and because phi 0 is 0, this thing here will go to 0 as t goes to 0. If I take now the average over a shorter and shorter interval, oops, you don't see that already. If I take an average over a shorter and shorter interval, which exactly what my integral does, it's exactly the average value of the function from 0 to a, okay, then it follows that as a goes to 0, this thing also will converge to 0. Okay, and therefore the supremum of these probabilities, mu n r minus a, 1 over a, can be made arbitrarily small, because if I want to bring this further down below epsilon, then I can pick a large enough a that makes this part as small as I wish. I can take care of high numbers n by the convergence to the small numbers, so for all high numbers n this will be as small as I wish, and the remaining finite number of mu's I can take care of by taking a to infinity or enlarging a even further. So that proves tightness of the sequence mu n. If I have tightness of mu n, then I can turn back to lemma 2, which says that if I have tightness and I have the phi's having a limit, then actually weak convergence holds. So by lemma 2, using tightness and that I have limit of the characteristic functions, lemma 2 now tells me that there is weak convergence of mu's to some limit. Okay, and if I have weak convergence of mu's to some limit, then of course bounded convergence test functions like exponential itx will converge under the expectation, and then I know that phi n must converge to phi, which is the characteristic function produced out of mu, and that's the end of the proof for the continuity number.